Hello, good afternoon, everyone. Welcome to our fourth UFMRM webinar. Today, we are very glad to have Mike Gibson, Dr. Mike Gibson, to talk about the CADDIES model. So now the floor is yours, Mike.
Thank you, Albert. Hello, everybody. So yes, I'm going to talk about the accuracy and computational efficiency of CADDIES cellular TomTom model, basically. So there's a couple of slides here at the start about the available data I'm going to skim through. Otherwise, this is going to be a bit of a whistle-stop tour. So yes, otherwise I'll talk about the cellular TomTom model and the complexity of that and how time step, resolution, flow limiters turn into the speed, basically, and an accuracy trade-off. So some of the recent work I've been doing is with flood bursts, specifically coming from pipes. So we've got a large amount of pipes in the UK, over 700,000 kilometers, but bursts can happen anywhere along those lengths. So we normally do it every 50 meters, 10 meters, 100 meters, but this leads to a lot of simulations that we need to do. So there's two ends of the scale here. We could either use fully computational fluid dynamics, which would be very, very slow. We'd be talking possibly hours or days on a supercomputer to do one simulation. Or we could use 1D routing, which is assuming that the water is going in one direction and will pond roughly around that, which is very quick, but not very accurate at all. This is the sort of thing we're looking at specifically. Pipe bursts, they can cause a lot of damage to residents and costs to the water company. So in order to assess the risk, we simulate these available data. As we know, we've got a lot of 1 meter high resolution data. It's freely available from the Environment Agency in the UK. And of course, we've got to worry about assets like trees and buildings. So this is a flood run on the DTM or DSM. This is the one with trees and buildings and everything in. Yes, even people. But we can remove all of them. Unfortunately, we've removed the building. So what we can do is add the buildings back in from the Ordnance Survey map. Here's a bit of a simulation using the CADDIES system. Pour down the road there. So yes, we can identify the buildings, prepare terrain, and then add the buildings back in. But the interesting bit I wanted to concentrate on is the cellular TomTom and how the system actually works. So it's based on a cellular TomTom, which each uses a grid. Each grid cell is a cell, has a certain state. In the game of life here, it's a simple on and off, but we have a continuous state in the CADDIES system to represent the flood depth or the terrain depth. So each cell carries out a simple rule using its neighbors to find out what it'll be in the next iteration. And we can do that in parallel for every cell in the grid. And from these simple rules, we can get very complex emergent patterns, basically. So the CADDIES system is open source. It's actually an API designed to facilitate the design of these local rules and then to run them on different types of cellular TomTom and different parallel hardware. So it's many call GPU or a multi-core CPU, square or hexagonal grids, for example. So when we're considering flood depth, we effectively have two values in each cell. We have the terrain depth or the terrain level and a water depth. Add those two together and you get the water level. And we are using the von Neumann neighborhood a two-step process. So in the first stage, we calculate the outflows for any neighbor that is lower than the main central cell. And then we write these outflows into a grid of edge buffers. And then in the second iteration, for every cell, we remove outflows and add inflows. So this way we maintain the water balance in the entire grid, assuming it hasn't disappeared out of a no data cell or something. So in the local rule commonly uses some variant of the Manning's formula, which is an open channel river flow formula to describe this flow between one cell to the next. But there are quite a few variants on the local rule. Part of the problem is that if you use a too higher time step with these rules, you get the Courant-Lindemeier condition, where basically if you use a too high a time step dependent on the velocity and the cell size, then you get an oscillation which spreads across the entire grid, destroying the quality of the simulation. Is we have a weighted model. So this local rule uses the Manning formula only once on the steepest neighbor, and then it uses the water level difference on each of the other neighbors. And it also critically leaves a small proportion of water in the main cell to try and counteract this oscillation, so it's equal to the smallest outflow. So if we can use a larger time step, we could take less iterations, and the complexity is basically based on the number of iterations we've got to take. So if we could use a higher time step, or if we can use a simpler rule or less cells. So an alternative rule, the Hunter-Bates rule, uses a flow limiter based on the time step. It's a similar sort of concept, but you're going to get this problem where if you use a much larger time step, you will get a quicker processing time, but you won't get as much propagation. So instead of this checkerboard oscillation, you simply get a lesser quality of the simulation. So this is a 2000 millimeter pipe burst that we've simulated, and we've simulated it using InfoWorks, which is the one in yellow, and we've simulated it with CADDIES, which is blue. And so we're using a minimum time step of 0.01 seconds here, and it takes 5 minutes 33 for us to process. But if we increase that time step, we've halved the time here, so 2 minutes 40 seconds, but we've started to lose some of the propagation. Not all of it yet. Time step further to 1 minute now from 5 minutes, so we're 5 times faster. We are losing some of the propagation. And at 30 seconds, even more to the extreme, as you can see now. I'm told you can't see it. Let us try and reset that. Duplicate. There we go. So, yes, do 15 seconds, but as you can see, the propagation there is terrible. So we can look at this as a trade-off. So dependent on so that was a 2000 millimeter pipe burst. So dependent on the size of the pipe, it depends on the size of the flow coming out. So it's a much larger trade-off between the processing time and the error on a much larger pipe. So this is starting with a 100mm pipe burst. I show a few seconds of each pipe with CADDIES here on the left and InfoWorks on the right. So InfoWorks is using a triangular irregular mesh. So of course that can have variations spatially on the quality. So I've tried to keep a roughly the same number of cells, but that can cause local spatial variations. I must admit, I thought this was a river, but we will see later. So yes, using a triangular irregular mesh, you can change the resolution spatially, but the problem is that it is an irregular mesh, so you don't know which neighbours you're going to get ahead of time. So using a CPU here, using our very slowest time step, we are actually slower than InfoWorks. As we've seen, we can increase that speed using a better time step. Where if we go onto the GPU, we're actually using the same slowest time step much quicker than InfoWorks. This is because we're using a regular mesh, which is basically better suited to the many thousands of cores on a GPU. InfoWorks is also using a single point precision floating point on the GPU, which is kind of cheating because it makes it go twice as fast. And we can show this here with us using double or single point. So on this very large scale test case, we've got InfoWorks on the GPU taking 20 minutes, and CADDIES will take about 3 minutes, where if we increase the time step, we can get it down to 1 minute 46, half the time, keeping the mean error below sort of 10 centimeters. What we don't want to do is go right up to a 1 second minimum time step, which is obviously not very good quality. So we have actually quantified, given a certain tolerance of error, what is the optimal time step for each given pipe size. So you can see that we've got much larger savings up on the larger pipes as well. So instead of taking sort of 350 seconds, we can get down to 100 seconds, and we've lost very little error. So 2D reduced complexity models are capable of creating highly realistic models very fast, and we can quantify this. So you'll hear a lot of papers which say this model is much faster, or it's more accurate. We need to know both how fast and how accurate at the same time. I'm told you've lost. Try and get that back. Okay. So yes, a regular grid gains a much better speed up on a GPU. We can use single precision on a GPU, and that will gain approximately twice the speed up. and rules should be judged in terms of this trade-off. So the last little bit, we have been transferring CADDIES into industrial partners, ICS, which is consulting here in the UK, for large-scale usage of it. We're also looking at hexagonal grids, which was a previous presentation. So I'd be interested to look at the trade-off for the hexagonal grids compared to the square. And we've been running large-scale test cases on London. Last but not least, the slightly boring DSM and coloured that we've been looking at. This is the same test case. Through Google Earth, so you can actually get more of a feel of where it is. A big flat patch we flooded was Sheffield United. So it's a hypothetical test case. So you see there's some ponding there on the subway. It's quite realistic. Try that again. So we can see we've hit a river there. Some more consideration modelling wise for rivers. Of course, we've modelled that as a dry river. Interestingly, up here, what I thought was a river is actually a railway station. Just shows you how the key to engagement is full visualization. Gone again. Wonders of technology. So future work is to explore the trade-off between different state transition rules, or the same rule with different cell shapes, for example, hex grids. So we need to look at other parameters other than just the minimum time step. So the alpha parameter, which scales the time step linearly over the entire simulation. Things like maximum slope. So we're also going to look at animation in real time on the GPU, 1D, 2D linkage with sewers, optimization of CADDIES to run on multiple GPUs. So using a network, we have the problem of communication. And at the moment, I'm working with serious gaming, just looking at optimization problems and human interaction, machine learning. Thank you very much.
Apology. Apology. Sorry. Thank you very much, Mike. And that's sorry about this technical issue we have today. Mike talked about the CADDIES model that we have developed together in Center for Water System. So I suppose there might be some question regarding the work, and I'm also appreciating that new audience from the different part of the world. So hopefully, if you have any question, you can pop it now, please.
Hello, thank you for the interesting software. I am participating in this webinar from York University. I'm wondering, how can I ask my question? Is that in mic or I should type it?
No, you can just ask now, no problem.
I want to see is this modeling can work for rainfall events, or is it just for pipe bursting?
No, we can run that for rainfall events or for these inflow events or for dam bursts as well.
So it can work for rainfall events too?
Yeah.
Thank you. And have you considered soil characteristics in this modeling? How you consider it? Because I'm asking, for example, if you have a huge area sand parking lot near the pipe burst, it can absorb any water, and it cannot go furthermore in the other neighborhood areas. I wanted to see, have you considered soil characteristics in the area? How did you did it?
Yes, the CADDIES model can consider what we call infiltration, so have a water absorption rate per cell. So it's just a case of supplying that data then to the soil characteristics.
May I know what is the equation is used for infiltration? Is that SCS?
So you provide a hytograph, so that's steps from one rate to another, but basically you're providing the rate per time.
Yes.
And then we just remove that water given how much time has passed.
What is the approach of removing the water to the soil? Is that green-amped or SCS or other kind of equations? Or
so as I say, you're just you provide the rate, and then we're just removing that much water, if that makes sense.
So that is just user-defined rate?
Yes, yes. So at the moment we don't have any equation system to judge it. We could develop CADDIES to store the water that's removed and then have some kind of equation to have the infiltration based on how much water has been absorbed. That's plausible, but at the moment you just provide the rate.
And the rate can be provided for each type of area, or it is just for all watershed that you are modeling? It is
for
just
each
one
individual cell you can tailor that. So for every 1 meter square in your terrain.
1 meter square.
Yeah, yeah. Depending on your resolution. So.
Thank you for your answers. It was helpful, and thanks for your interesting software. It is great.
Thank you.
Do we have more questions?
Yes, hi, I'll ask another one. Yes, Julian Lom from XP Solution Innovize. Thanks, Mike, for the presentation. That was very interesting. I didn't have quite the time to catch the time step condition. It was one of the earlier pages, but I wasn't quite clear if the time step condition is checked as a local rule or as a global rule.
So that is checked as a global rule because you need to have the same time step across the grid. However, you can adapt time over the time of the simulation. So basically, we've got a setting in there at the moment. I think it's every 60 seconds of simulation time. It will check the flows, find the largest flow, and adapt the time step for the next 60 seconds worth of iterations.
Oh, okay, so you update the time step every 60 seconds, basically.
Yes, yes.
Okay. And presumably that's a user parameter, these 60 seconds.
Yeah.
Okay.
So you could increase that and have a more static time step, or you could decrease it and have more adaptive. But the problem is yes, you need to get the biggest flow from the entire grid, so you lose the parallelism at that stage. So if you have it updating too often, you can really slow it down.
Yes. Yeah, of course. Yeah. And well, that's related to my second question. You mentioned in response to the first comments that you can represent dampers with this approach. Have you done any testing on dam break flows?
I believe we have. I'd have to find you the papers for that, but yes, I believe we have done.
I'm quite surprised that you would have good results on dam break flows, considering the important role of inertia for dam break flows, and presumably this is not captured by CADDIES.
No. So the simple weighted rule is not using inertia. It's assuming that most of the inertia is cancelled out by friction, of course. We do have an inertial type rule in there that tries to compensate, but no. So it's reasonably realistic, but again, it's a question of how realistic and how fast, of course. So, yes.
Yes, back to the trade-off. Yeah.
Indeed.
Okay, great. Thank you.
Thank you.
Thanks, Julie. Do we have more questions? Before we got the next question, can I just quickly respond to one of the Sarah's question about the infiltration rate. So the idea for us to implement this very simple rule for CADDIES because we want to speed up. That's why we didn't implement any this kind of green amp or any other types of soil infiltration equation, because they will require more computing time and also require more memories that will slow down the performance of the CADDIES.
Yes, thank you.
And do we have any other questions? Okay, if not, and I would like to thank Mike for his excellent presentation, and thank you audience for your participation. As usual, we have recorded the webinar, so it will be shared together with the slides on the website and on YouTube. So you will get the link with all this information, and we are looking forward to seeing you for next webinar. Thank you very much.
Thank you, everyone.
Thank you.
Thank you.